Okay folks, so in this video we want to look at the graphs of the cosecant and cotangent functions. I'm going to work through the graph of the cosecant function with you, but I want to let you know that when we get to the cotangent, I'm actually going to let you explore that one on your own. You're going to try your best. You're going to use your earlier trig function graph handouts to help you with it. So at this point we've looked at the graphs of the sine and cosine, and then we've looked at the graphs of the secant and tangent. And I recommend finding all of those graph handouts. They were all pre-works to help you with the second page here. I think that if you were to look at the patterns and similarities, you can figure your way through that second page using your earlier handouts. But let's go ahead and dive into the cosecant function. So the cosecant function takes inputs, but not from the entire real line, because the cosecant ratio is the output ratio. One way to look at it is if you give a right triangle, it's the output ratio of the hypotenuse side of a right triangle over the opposite side. And if you think about that in terms of values on the unit circle, if instead of thinking about it as sides of triangles, you think about it as ordered pairs on the unit circle, you've got all of these different ordered pairs that you could possibly construct the cosecant from, but there's a problem. We're dividing by the opposite value, and the side of the opposite, if you construct a triangle here, that value here in terms of x and y, well, the cosecant of theta is equal to the hypotenuse, or the 1 on the unit circle, divided by the opposite side, which is the y coordinate on the unit circle. And so we can see that this function is never going to be defined whenever y is equal to 0, and that happens at two key locations on my unit circle. The y coordinate is 0 here and here, and so the cosecant function will not be defined at those values. So it takes real numbers from the set of x, such that x can be any real number, except that we can't have the input be, what angle is this? This is the angle 0, this is the angle pi, the angle 2 pi. So the inputs to the cosecant function cannot be multiples of pi. And that's for an integer. And I never quite have enough room to fit this. And that's measuring x in where x is measured as a positive angle, or x is measured as an angle in standard position. I want to point out that there's this confusing aspect here, that when we're on the unit circle, we have the ordered pairs of the unit circle that are used to construct the trig ratios along with the hypotenuse. And when we talk about the unit circle, we label the angle on the unit circle as theta. And so we do say on the unit circle that the cosecant of theta is equal to 1 over y. But when we're on the when we're just dealing with inputs, outputs in the traditional sense, we choose to use our input variable x, and so x is not playing the role of the x coordinate on the unit circle. It's playing the role of the angle, and that's just a confusing fact of life, folks. I know that's tough. Okay, so let's say it again. What's the domain of the cosecant function? The domain of the cosecant function is a set of numbers x, such that x can be any real number, except that x cannot equal n pi for n an integer. The range of the cosecant function, as we're about to see on the graph here, will be from -infinity to -1, and again from 1 to infinity. I chose to do this in set builder notation because we have infinitely many points we need to eliminate. This was easier to write in the traditional interval notation. So I think before we go any further, let's go look at the graph of that cosecant function and see how we construct it. Okay. So for example, if we were to evaluate some points on here, if we were to go find the, say, the cosecant value of pi over 2, what we would do is we'd go on our unit circle, and we would go to the angle pi over 2, which is right there, and we'd give that ordered pair, which is the ordered pair 0, 1. And so when it comes time to give the cosecant of pi over 2, we're going to give the ratio of the hypotenuse, which is 1 on the unit circle, or the r value on the unit circle, which is 1, divided by the y-coordinate on the unit circle, which in this case is also 1. And so we get that the cosecant of pi over 2 is 1. That means when we inputted pi over 2 into our cosecant trig function, we got out the output value of 1. We could do some more ordered pairs on here. So for example, we could go find the cosecant of pi over 6, which is equal to 1 over, here I'm going to do it a different way. I could go back to my unit circle. Here I'm going to write it as the sine of pi over 6 inverted, and the sine of pi over 6 has a ratio of 1/2, and so the cosecant of pi over 6 is equal to 2. So there's, I can get the values immediately from the unit circle, or I can get them by using various identities. Regardless, we know that if we plug in pi over 6 into our cosecant function, we're going to get out the output value of 2. Let me just put a couple more values on here. If we plugged in pi over 4, we would get 2 over the square root of 2, and if we plug in pi over 3, we would get 3 over the square root, 2 over the square root of 3. Folks, you'll notice I didn't choose to rationalize these denominators. You can do that. I actually like to leave them in this improper form. I think it's a little bit easier to remember the values, and I won't require it. My math lab, though, however, will ask you sometimes to correct that. Now let's go look at the domain restrictions on the cosecant function. We can see that the cosecant function is not defined for integer multiples of pi. And one way we can see that is the argument that we gave just a second ago. If we went to go find the cosecant of 0, it would be 1 over the y-coordinate at the angle 0, but on my unit circle, the y-coordinate at the angle 0 is 0, and we cannot divide by 0. There's lots of other ways to thread the needle there, but that's one quick explanation. So regardless, we just said that at the angle 0, the function is not defined. We see that indicated in the graph of this function. And one thing we could do some work, and we're going to need a little bit more work to help us with this, but in your calculus class, you'll learn to explain why we have these vertical asymptotes everywhere the graph of the cosecant function is undefined. Okay. Let's label those vertical asymptotes at x equals 0, x equals pi, x equals 2 pi, x equals 3 pi. Here you can see what I mean by we have asymptotes at multiples of n pi for n an integer. So there's our graph of the cosecant function. Okay. So let's say a few more things about the cosecant function. The cosecant function is not continuous on the entire real number line. Well, we're not going to define exactly what that means. Roughly speaking, it means that we can sketch the graph. When we go to sketch the graph, we would have to pick up our pencil. Okay? More specifically, the cosecant of x has vertical asymptotes at all values where it's undefined. And we just said that the cosecant function is undefined at all of these integer multiples of pi. The cosecant function is an odd function, and meaning that f of negative x is equal to negative f of x. Another way to say that is that opposite domain values always have the opposite range values. Let's just go see what we mean by that. I want to highlight this point right here. We found that when we plugged in pi over 6 into this function, it spat out the value 2. If we were to plug in the value minus pi over 6. So what am I doing? Instead of plugging in pi over 6, I'm plugging in pi over 6's opposite. Because cosecant is an odd function, or illustrating that cosecant is an odd function, when I plug in the opposite domain value, I get out the opposite range value, and the cosecant of minus pi over 6 is minus 2. So minus pi over 6 comma minus 2. That when I change the sign on this value, I got out the opposite sign for the paired range value. That's what we mean by an odd function. That happens for all ordered pairs, not just the one I selected, and so cosecant is odd. The cosecant of x is said to be 2 pi periodic. Let me do that in the same color. The cosecant of x is said to be 2 pi periodic, meaning that f of x is equal to f of x plus 2 pi. Adding 2 pi to any input value still returns the same output value. The graph repeats itself every 2 pi units. Okay, folks, that was a little bit lengthy, but that was our in-depth look at the graph of the cosecant function. I do want to add one more thing. I was able to construct this graph of the cosecant function just by plugging in values, but I want to point out there's a similarity between the cosecant function and its reciprocal function. If I were to sketch its reciprocal function, which is the graph of the sine of x, here is the graph of that reciprocal function here. And so sometimes when I go to construct the graph of the cosecant function, I choose to draw the graph of the sine of x and then use that to aid me in the construction of the cosecant function. Notice that everywhere the sine of x was equal to 0, that's where precisely the cosecant function had its vertical asymptote. And for example, on my sine function, here I've got the ordered pair pi over 6 comma 1/2. If I take the output from pi over 6 and invert it, I get the value for the cosecant of x. So the reciprocal of 1/2 is 2, and that's true for all of those other values on the graph of the cosecant function. Okay, folks, we'll pick this up in the next video. Thanks for your patience.